Good afternoon. When it comes to structural concrete, internally reinforced with non-corrosive, non-metallic reinforcement, the low battery seawall, the reconstruction of the low battery seawall in downtown Charleston is the largest civil infrastructure application in the state of South Carolina. So I'm pleased to share with you an overview of this project, particularly with respect to sustainability and resiliency attributes which are at the core of the vision set forth by the City of Charleston, the owner of this infrastructure. And I'm also pleased to do so on behalf of my co-authors. That you see the pictures here. It's a pretty diverse team in terms of background and expertise, and we have Brett, Laura, Ryan, Jim from JMT on the side of the structural design and the management of the project. Again, I'm focusing here on the structural concrete side of the story. This is a much larger public infrastructure project with different facets, so we're focusing on this side of the story. Dave, Hartman, and Danielle, who's also here, on the side of the non-metallic reinforcement. Dave actually is the one who brought us together in a way. And then Josh Beach from the contractor side. And last but certainly not least, probably first, Mr. Frank Newham, who recently retired just a few weeks ago from the City of Charleston. And the City of Charleston and Mr. Newham in particular are really responsible for making the vision become a reality of using kind of an innovative material, certainly innovative material from the standpoint of engineers and contractors who might not be as knowledgeable as some researchers on this kind of innovative materials, but they were able to do so and bring this material into the field, and they did so, I'm saying in a visionary and brave way, also because they did so without the availability of a code, so only with the use of a guide. So we'll see some of the implications of these choices. So the low battery seawall stretches for about a mile in the waterfront, in downtown waterfront of Charleston. And you see here, this is a picture just to give you an idea how scenic the area is. I'm smiling because it's my favorite spot in the city. Plenty walks over there and a bunch of detours just to have one more walk over there. So this is the location. This is a picture done during the construction, and we'll see some interesting aspects from the standpoint of application of non-metallic reinforcement peculiar to this project. So we'll go through the objectives and the significance in the context of sustainability and resiliency, the scope of work. So what are the different steps that were involved in the construction of the reconstruction of this seawall? The structural design and detailing, constructability considerations. This aspect was particularly important, and I think it's a valuable thing to do, or something precious that a field project brings that research projects done in the lab cannot. So the experience in the field, what can we learn from an actual application, even more so in this case of this magnitude? So we will look into the constructability, and then briefly the material cost. I added this particular point. There's something interesting to see, but there's also some interesting discussions when you talk with the contractors or designers. Oh, what is the cost of the material? Is it really going to make a difference? But the reality is that it does make a difference up to a certain point, because what really matters is the cost of the overall operation, the time that it takes. So we'll see some of these trade-offs and how they play out throughout the course of this project, and then briefly some takeaways. If I can go on, which apparently I can't, but I'll find a way. It's amazing, engineers. 50-50 chance you usually go from the wrong one, but I got the right one, this one. So, glass FRP bars, I don't think I have to go through the basics of these materials. Some points, though, some particular characteristics that actually play a role in the interpretation of what we saw in the field through this project. So, relatively low elastic modulus in tension, we all know that, even with the new generation FRP bars, and the linear elastic stress-strain response up to failure. So these two mechanical aspects play an important role in the flexural and shear design. For example, for the case of this foundation slab, which supports the entire structure of the seawall, how feasible is it to build a counterpart, GFRP reinforced concrete slab, structural slab, as opposed to a steel reinforced concrete counterpart? Do we need larger dimensions? Do we need more concrete? Is the reinforcement going to be too congested? How is the detailing of this reinforcement going to play out? Is it going to be practical? So there are a number of design, so structural and feasibility, so constructability points that this type of experience helps to answer to or helps to understand better. Non-corrosive reinforcement, electromagnetic transparent, we all know these things. Lightweight, this is important from the standpoint of constructability, actually more than I thought. So we'll see why, we'll see. And we got this in one of the previous presentations. The presenter was actually mentioning the speed of installation. We'll see some information thanks to Josh Beach from the contractor side. And I added this point related to the state of the art, just to convey the fact that we have had guides for a while, thanks to ACI. We have design codes for bridges published in 2018, the second edition of the AASHTO LRFD specifications. We have the ACI code published in 2022. At the time of design of this particular seawall structure, there was no code that the designers could use. So this is the reason why I noted the point of, let's say, the bravery, if you will, of the owner in just embracing innovation while at the same time not being too intimidated by the lack of a code, also considering the quality, but this is just my opinion, of the guidance that was provided by the ACI 440 document. So here you see a picture of the slab, which we will discuss briefly in the next few minutes also. And this is the seaward side of the seawall, where in the beginning, GFRP reinforcement was used only on the seaward side. So this is the point I'm making with this slide. So this is the about 1 mile length of low battery seawall. The project was divided in 4 phases. So the first 2 phases here, it's about 2,000 feet in length. They entailed the use of GFRP reinforcement only on the seaward side of the seawall. That's the part that is perhaps most concerning, that used to be more concerning to the designers, whereas for everything else, steel reinforcement was used. Things changed in the 3rd and 4th phases of the project as the owner and the designers, with the agreement of the contractors, they moved entirely. So this is about 3,000 linear feet in this area here. So they moved entirely to GFRP reinforcement. So we'll see the reasons why. So in regard to the objectives of this project, the mandate of the city was to enhance sustainability and resiliency with respect to a number of aspects. So first and foremost is longevity. Longevity with respect to corrosion. We'll see a couple of pictures that I took in the summer of 2020 in a minute. The damage to the concrete, you see here, longitudinal damage associated with subsidence of the soil, so soil seeping out here, and what is the result of this? Well, you can see that the walkway here is not exactly straight. So that was a significant concern, also because there are water lines running underneath this seawall. So there were a number of practical issues of significant relevance. Structural safety and adaptability in terms of climate, adaptability in terms of the increasing frequency as well as the severity of extreme events, in this case, flooding. We'll see some information shortly when we'll discuss the structural design and detailing. But the point here is, from the standpoint of the scope of work, to raise the top of the wall of the existing seawall by about 2 feet. So looking at the next 50 years sea level rise, but then in addition to this, consistent with the US Army Corps of Engineers projections, to accommodate an increase to a total of 13 feet in height. And this is how the entire structure, the supporting structure of the seawall, was designed, looking at the next 50 years. And then, certainly important is the functionality. So not only drainage and flood protection, but also accessibility in particular accessibility with respect to the low battery side and the high battery, which used to be kind of separate in terms of height, and now they're brought up to the same height. So much easier accessibility and comfort for those enjoying this waterfront. So here's the pictures I promised regarding corrosion. This was in the summer of 2020. This is just to give an idea of the condition of the seawall. And this is, as we saw in previous presentations, nothing new, but the point here is this can happen in a matter of 20, 25 years. It's nothing strange. And building with a similar technology would bring up the same issues sooner or later. And this is also important from a life cycle cost perspective related to maintenance. Now, when it comes to the increased frequency and severity of extreme events, here are just a couple of numbers to give an idea of the magnitude of the concerns brought up by the city. So sea level rise, so almost 2 feet in 50 years. These are the projections, but the projections are already real when it comes to facing some of the most extreme events. For example, you see here a picture taken during the peak tide during Hurricane Matthew. In a few minutes, I'll show you another picture taken during Hurricane Irma, but this is the situation under these events along the seawall. So the scope of work entailed, first of all, raising, as we said, the top of the wall to enhance the resiliency of this public infrastructure project over the next few decades. And at the same time, changing the kind of supporting system that we have here, or foundational system, where instead of relying on timber piles and a timber mat on top of which the concrete system was built, micropiles were used to actually support, standalone, a foundation slab on top of which the rest of the seawall was built, filled, and then topped with a slab on ground. So a fundamentally different type of structural system. This is a picture of the first phase, from the first phase of the project. I was not involved yet. And here you see the first part in the part that is more to the left of the original picture I showed a few minutes ago. But I wanted to go through the steps of this field application. Briefly, step one entailed the removal here of the riprap, the excavation below the mud line, and the exposure of this concrete skirt. And the purpose here was, first of all, to remove concrete that was damaged or unsound, and we saw some pictures before. There's plenty of it. There's also plenty of concrete that is corroded because of the reinforcement that used to be there. Part of the concrete was without steel reinforcement. Something interesting, by the way, I'll go back just for a moment. Something interesting is that part of this concrete was completely without reinforcement, and the original wall was built over a century ago. It was completed in 1919. The concrete was just as good as new. Now, the second step entails the cutting of the old wall for the purpose of building on top of it the rest of the supporting system and the seawall. So this was done starting from the third step. Here you see the introduction of the micropiles and the resurfacing on the seaward side using GFRP bars. This was done throughout the entire length of the project. So seaward side, all with GFRP reinforcement. So a few pictures on the different phases, on the different steps here. Step two, the cutting and the removal of the old seawall. And then this is taken from the third phase. This is the third step, showing the GFRP reinforcement as a skin reinforcement on the seaward side that is shotcreted as well. And then 3 more steps. So, and here we get really into the structural side of the story. So a bottom slab here with 2 great beams built in, running through the entire length of the seawall as a support away from the micropile locations. And in phase 1 and 2, this foundation and this rest of the infrastructure was built using steel reinforcement, whereas in phase 3 and 4, everything moved on to GFRP reinforcement. So we'll see why this is one of the major takeaway from this project, the change in plan by the owner as well as the designers with the agreement of the contractor. So the 5th step entails the construction of the seaward wall portion as well as the landward wall portion. You see them here and here, followed by the filling and then the preparation of the installation of the slab on ground. Again, in phase 1 to 4, for both of these steps, GFRP reinforcement was used. Again, the reinforcement that is more exposed to the outdoor environment or to direct exposure to seawater. But arguably, from a structural design standpoint, the main challenge or the most interesting component here might really be the slab with the great beams that are built in, and that's what I'm going to focus. Also, because of time limitations, we'll focus on that side of the structural story. So some more pictures from these different steps. So step 4, the foundation. Step 5, the seaward side of the wall. And then step 6, the topping with the slab on ground. And these are, by the way, from the very last phase of the project that was completed recently, phase 4. So regarding the structural design and detailing, as far as the design loads, you see the provisions that the designer used, and we wanted to give you a sense of the loads we were dealing with in regard to design. So impact, breaking wave, and hydrodynamic load. And then regarding design strength, this is what we used as far as provisions. In addition to, when it comes to material properties, focusing or using the specified minimum strength provided by ASTM D7957 instead of the properties provided by the manufacturer. This makes a big difference also in terms of design. What difference? Well, briefly, this is the summary in terms of reinforcement and then load demand and design strength for the slab using the steel reinforced concrete option used in phase 1 and phase 2 of the project. So for example, for the positive moment reinforcement, number 9 spaced at 7 inch on center, whereas for the GFRP reinforced concrete option covered in phase 3 and 4 of the project, here you see more reinforcement, so number 8 at a 4-inch spacing. So more area certainly, but a much smaller weight. That's going to have a significant effect in terms of constructability. But also, remember the properties I mentioned in the previous slide, using properties actually from the COA, so the ones provided by the manufacturer, obviously minus 3 times the standard deviation, as most of us, I believe, know. This spacing can also be increased by 50%. So the point here is there is actually margin to use even less reinforcement. So we're far away from the limits when we design with this kind of materials. And by the way, the thickness of the slab is the same, which is not a foregone outcome given the sensitivity of this of the structural components to shear failure. Despite of, well, I wanted to make a brief comment, despite of the significant over-conservativeness of the VC equation, not only in the ACI 440 guide, but also in the ACI 440 code. But still, despite of these limitations, we can still have these practical outcomes. Now, regarding the detailing, well, these bars, first of all, they cannot be bent on site. We all know that. It's a limitation. Is it? Maybe it depends on the kind of application. In this particular project, it turned out the workers, the field crews, didn't care that much. What they did care about is the lightweight of these bars. They had no problem with pre-assembled or pre-prepared details by the manufacturers. And when I say pre-assembled, I'm talking about U-shapes for the terminations rather than bent bars. I'm talking about C-shape assemblages instead of bent stirrups on site, and you see the counterpart details for the steel reinforced concrete alternative here in the bottom sketches. So the result here between steel and the GFRP option is still a reinforcement layout that remains practical. Regarding constructability, and I'll cut a little bit short. Oh, thanks. So 2 minutes. It's not too bad. So I'm good then. So in regard to constructability, the lightweight is important because it allowed workers, and this is actually by their own initiative, to build prefabricated cages and just drop them fairly easily where they needed to be. The alternative was to move around much heavier bars with the use of forklifts, cranes. In this particular project, they were using excavators, so this made the field crews particularly happy. And then the standard placement operations, which mirror those we use with steel reinforcement. So this prompted or helped with the familiarity and the confidence of the crew that experienced this kind of reinforcement for the first time. So you see here the cages for some of the grade beams and the cages here for the slab on ground. So regarding constructability, time saving, I'll fly through this slide, but it's an important one. These two pictures are significant. They are provided by the contractor showing that in the span of a 2-hour shift, for 140 feet length of seawall, the wall was cut, 4 more was installed, GFRP reinforcement was installed, and 1 more 8-hour shift, so a total of 3-hour shift. This portion was completed the following day in the afternoon, whereas for the same length, 140 feet, a steel reinforced concrete counterpart would have taken 6 8-hour shifts, so a very significant change in terms of speed of installation. Regarding the material cost, because of time limits, I'm going to go even faster here, but suffice to say that the winning bid for the 3rd and 4th phases of the project, when the owner, together with contractors and designers, shifted entirely to GFRP reinforcement, while the winning bid for the 3rd phase was the same cost of the steel reinforced concrete plus $1. That was the winning bid for the GFRP reinforced concrete option. So traditional bid letting process, still a competitive solution, and this, at least in this particular project. So here are the takeaways, and I would like to highlight just the last 2 here. So the project transitioned from a hybrid solution in phase 1 and 2 to a fully GFRP solution in phases 3 and 4, just because of the attributes of not only strength, stiffness, etc., but also constructability of this type of solution. And then the GFRP works, in particular, GFRP work in phase 3 was completed in 7 months instead of the budgeted 14 months that were originally considered. So this is just a closing slide, just to let you know that the City of Charleston, based on the experience of the Seawall project, decided to use GFRP reinforcement also for this particular bridge that was replaced recently in Daniel Island in Charleston. Thank you very much.